Welcome back, everyone. This week we're going to talk about all the settings when you go through the app, all the different settings for programming the inverter and what they all do. We're going to talk about which ones are important to change, what some of them do, the important ones, and which ones you shouldn't be adjusting. There's some that should just be left on factory defaults, except in very certain circumstances, and you just don't want to touch them. So we'll go through all those different things and what to do. When we look at the app, we've got a bunch of different menus we can go through. Most of what we're going to be talking about today are under settings, and then we'll talk a little bit about equipment maintenance. The energy is kind of the displays of what the inverter is doing. We have a different webinar on that. And then logs showing your error codes and any saved alarm messages. And then switch is just changed to a different inverter. Equipment maintenance, that's where we can most importantly sync the device time with the with our phone or our tablet that we're using connected via Bluetooth locally. That's only applicable when you're locally connected. Reset takes everything back to the factory default conditions. This is useful if you've been going through settings and you can't remember what you changed and nothing's working right. Take it back to factory default so you can start again. And then clear all data. That's generally when you're going through these settings, once you've got everything set up like you want it to be and the inverter's behaving correctly, then you do a clear all data and it gets rid of any bad monitoring data that's been produced when the inverter first turns on and it doesn't have all the correct sensors hooked up or isn't programmed quite correctly for the situation it's being used in. That can generate some bad data in the monitoring files. So once you get it fully programmed, if you clear all the data, it clears that out. And then you can start fresh so your monitoring will be more accurate. Moving on to settings, where we're going to spend the rest of the time today. We have a bunch of subsets in here. Power control, that's where a lot of our settings that we're going to be modifying are going to be. Battery has a lot of settings to modify as well. General has a few settings, grid has a few settings, and communication, that's where we set our Wi-Fi. Just to go over that a little bit, we've gone over this a little bit in the webinar on commissioning an inverter, but we're going to repeat it here. This is where we set our Wi-Fi connection. We can scan for Wi-Fi networks, enter the password, and connect to it. Just a reminder, it only works for 2.4 gigahertz networks. It doesn't work for 5 gigahertz ones. And it doesn't work for ones that are meshed with 5 gigahertz and 2.4 together. This can be some of the new Starlink routers and other newer routers. It needs to be a pure 2.4 gigahertz signal for it to connect to. It doesn't work with open networks that don't have a password. It has to have a password to know what it's doing to connect. And we have also had some issues with some routers which are programmed to block connections to foreign servers. The server is actually in the US, but it's run by a foreign company. So we've had some issues with it blocking connections to the server in certain cases. So those are some of the communications issues. You can always use a LAN connection straight onto the dongle rather than the Wi-Fi connection. And then you don't have to worry about any of the Wi-Fi issues. You do want to think about lightning protection for that Cat5 cable coming to the inverter. If you're running it from a different building, you'll want to have surge protection on that Cat5 cable because that is a point of entry into the inverter for lightning surges. Moving on to the general category, Here's where we have some of our anti-islanding things. We just leave them as they're set. We have our insulation resistance and leakage current settings. Generally, you don't have to touch these. They have to do with the tests the inverter does on the PV array to check whether it's got any leakage or ground faults. If you have an older, poorly installed array that maybe has if you've got an actual hard ground fault, you should repair that. But sometimes you'll just have older PV modules have a little more leakage current, and thin film modules can have a little more leakage current. So you may have to adjust these in those cases. If you've got broken modules that water is getting through the glass into the cells, obviously you're going to have a bit more leakage current there. Really, those should be replaced as well, but you can adjust this to allow use with some of these older modules or thin film modules that may not work with the factory settings, but usually the factory settings are fine here. We have a derating setting, don't change that. We have grid voltage type. This is actually a very important one. For 120, 240 volt split phase, what we're doing most of the time for residential systems, you want it on UL split phase. Don't set it to single phase. That'll set it to 230 volts line to neutral and then 0 volts on the other line. And if you feed this into your typical US distribution system that expects 120 volts line to neutral, you can blow up a lot of your equipment. So single phase is only for European or rest of the world type systems, not split phase 120, 240 volt systems. Default is UL split phase. So if you're doing standard residential, you don't need to modify this. For 3-phase systems, you want to set this to UL 2-3 phase. And that is essentially 2 phases out of a 3-phase system. 3 inverters together make up all 3 phases of it. If you're doing a 3-phase system, you'll set which phase each inverter is on. You're doing stacked systems on split phase systems, you just set that they're stacked, and that's in a different section. But you don't need to tell them which phase they're on because all of the inverters are both line 1 and line 2. Then we have a couple miscellaneous ones. The buzzer, generally leave that off unless you want the inverter making lots of noise and beeps when various things happen. DRM function, don't change that. Parallel mode, that's only for if you're stacking inverters. Turn on that. There's also hardware settings if you're stacking inverters. A little dip switch and obviously the stacking cables. So it's not just this software setting if you're stacking it. For the parallel system battery connect type, generally this should always be battery connect parallel, meaning all of the batteries are in parallel, not a single battery for each inverter when you have multiple inverters. You can set it up so each inverter in a stack system has a separate battery bank, but that introduces a lot of other issues because if you're not sharing loads and charging between the inverters equally, then those battery banks can get out of balance and not be the same state of charge. It's a lot simpler to just do it as a shared battery bank that all the inverters share. So the batteries come together into a battery combiner and then branch back out to your stacked inverters. If there are some special situations where you might want to do separate batteries, but 99% of the cases, you'll just want battery connect parallel with a shared battery bank for your stacked inverters. Going to grid settings, we've got most of these settings you're not going to want to adjust. Grid standard code, IEEE 1547. There may be some in the future some different drop downs for different island grids, which have different settings. For now, those are manually set in here. We have our maximum input from the grid, which is 24,000 watts, 100 amps for the pass-through. But you may want to set this less sometimes. One example of that is if you are trying to do peak demand, where you have a demand charge from the grid and you want to say, I never want to import more than a certain amount of power from the grid. You can set this lower. You might set it at 5 kilowatts, and then it'll use the batteries and PV as appropriately to power the load and never draw more than 5 kilowatts from the grid. If you do this, you need to make sure that you have enough battery and PV capacity to handle the load if you really reduce down that allowable amount of import from the grid. Another thing to remember on this is that it's uniform for all time periods when you set this lower than the maximum 100 amps. If you just have demand charges during a certain time period or want to limit your peak load during a certain time period, using some of the time-based controls might be a better application there. Another application of this maximum input power from the grid is if you're using a generator on the AC input instead of the grid, and that generator has less than 100 amp output, then you can set this lower down to not overload that generator. There's separate settings for generators going into the generator input, but if you got to get generator going into the AC in input, then you'll want to adjust it here to avoid overloading that generator with too much power. Two settings that we almost always want to change are the first boot and the reconnect and boot. These are factory default at 5 minutes, 300 seconds. And what this means is that when you turn the inverter on, it'll count down from 300 seconds before turning on. This can be pretty annoying that every time you turn the inverter on, it takes 5 minutes for it to turn on. So I almost always recommend that you go in there, change that to 10 seconds, which is the lowest allowable setting, and then it'll only count down from 10 seconds when you turn it on. If you're grid connected, all of these other settings are all protection settings for where it disconnects and reconnects to the grid based on frequency and voltage. And you don't want to adjust any of those unless you're directed to by the utility company or by engineers at Midnite. If you're on an island grid, you may need to change those grid protection settings. Often those have a bit more variability in frequency, so you may need to adjust those in order to work with the island grid. Also, if you are using a generator on that AC in connection, those tend to be, even large generators tend to vary a bit more in frequency and voltage than mainland USA grid. So you may need to open those settings up in order to make sure it stays connected to that generator. One important thing to note on running a generator into that AC in output is with some of the inverter firmware versions, if it sees a frequency of less than 56 hertz, it'll auto adjust itself to be a 50 hertz inverter instead of 60 hertz. The newer firmwares don't do that, but some of the older ones would do that. So if you hooked up a generator that was a little low in frequency, it could actually reset the inverter to be 50 hertz. And then we would actually have to go in from the factory command line control and reset it to be 60 hertz. So just something to be aware of if you are using a generator on that AC in is if its frequency is too far out of whack, it can cause additional problems. Battery settings, here's a lot of settings that we want to look at and adjust. For Midnite batteries, we just set brand to Midnite. Default will be pylon, which mostly works, but it's better if you set it to Midnite. Communications address 1 and capacity type SOC. If you are doing a battery such as a open loop lithium that you don't have communications with, or a lead acid battery, you'll want to set capacity type to voltage. And that'll bring up, instead of percent settings for most of the rest of these settings, it'll bring up all your voltage settings. If you're in voltage for your capacity type, the inverter still shows a percent SOC on the monitoring and on the front of the inverter. However, that SOC is not very accurate when you're in voltage type. So if you're in voltage type, don't pay a lot of attention to that SOC. If you're in SOC type, then that SOC is actually what's being reported by the BMS of the battery via the closed loop communication, and is a bit more accurate. There's still some situations where the BMS can be inaccurate, and we're going to talk about some of those in the programming we do about that. But for the most part, only look at the SOC if you're in closed loop. We want to set our discharge and charge 2%. This is essentially the range that the inverter will operate at. When it gets down to that discharge 2%, it'll shut off. This is kind of equivalent to the low voltage disconnect on an older voltage-based system. The charge 2%, that should generally always be 100%. Very few situations where we don't want to recharge it up to 100% when we're in closed loop. The battery is smart enough that it'll take care of itself. It won't overcharge itself. So we don't need to be intentionally setting it lower than 100%. One thing to remember is that this discharge it will go from on into standby when it hits this lower limit, 15% in this case, but it still is drawing power, still about 25 watts in standby. So even though the AC loads go off, it's still slowly draining the battery. So something needs to recharge it at some point. One thing can be a PV array can recharge it. Another is this next setting, the stop and start recovery charging when reaching percent. I'm gonna go back. So this start and stop recovery charging, this is essentially saying when we reach this level, and if we have grid power available, we're going to recharge the batteries a little bit, even if all of our other settings are generally saying don't use the grid for charging the batteries. These would generally be lower than the discharge 2%. So we're using power, and if we get down, like typically it would be 20% for our discharge 2%, and then this would be like maybe 10 and 15. So if it gets down there below, it shuts off the AC loads. But if the grid is present, we would rather just like top off the battery a little bit. So then when it gets down here, it will top off that battery from the grid, and we have our own maximum charge rate for just that recovery charge and a stop point for the recovery charge. So you might just top it off just a little bit at a low rate rather than at full power all the way to 100%. And that's just to keep, if everything else, something goes wrong with the programming and the battery is discharging even though the grid's present, we're going to use the grid to keep the battery from bottoming out. Another one we want to look at is minimum initiation startup battery capacity when off grid. It's a long, complicated name, but essentially what it is after hitting our low voltage disconnect, in this case, our minimum discharge, that we want to give it some time before we reconnect and turn back on. So if we turn off at 10% battery charge, We don't want to turn back on at 11% like it is here. Give it 5% to recharge a bit before all of a sudden we just turn the loads back on and suck it back right back down. That's a long, complicated name for what's essentially just the hysteresis on our low voltage disconnect for when it reconnects. Here's our recovery charging that we were talking about, and you can see our maximum grid recovery charge power. That's the watts that will do that recovery charge at. And then we have the starting percent. If it gets below that, it'll recharge from the grid and then stop at the higher voltage or higher percentage level. And this is really just an emergency catch to keep it from going completely flat if we've set something wrong in our other settings and we're discharging the battery too much, even though we have grid power available. If we don't have grid power available, say we're an off-grid system, then this is kind of not applicable. That was a duplicate slide right there. For battery settings, it's recommended to use at least 10% for your minimum discharge. We can go to 0%, and batteries, they protect themselves. They're not going to seriously decrease their lifespan if you do that. But what happens is you risk having the system shut down, and when the batteries shut down, it doesn't automatically restart. You have to manually restart it. If the inverter shuts itself off, then when the batteries recharge, either from the grid or from PV coming in up to that reconnect setting, it'll turn back on automatically. But if you get to the point where the BMS on the batteries shuts down, then you have to manually restart it. It's just like when you're driving and you've got an eighth of a tank of gas left. Should you wait for the gas light to come on before finding a gas station, or should you just refill? Depends on how much you want to deal with the potential repercussions of having everything shut off. If you're always on site and you're like, I'll just manually restart the battery bank if it shuts off, then you could have this set really low and it might just shut off. But if you're remote and you don't want to manually reset it or train your customer to manually reset it, it's better to always make sure that the inverter shuts off a bit above your minimum discharge. And what can happen is if you don't reach 100% state of charge regularly, once every week or two, then the BMS can actually drift off from reality. So very low loads on the BMS are essentially invisible to it. It can't see loads under about, I believe it's 1 amp. So if you have several batteries and a single inverter, just the idle load of the inverter is less than what the battery BMSs can notice. That doesn't mean that they're not slowly discharging, but they'll continue saying 100% SOC if all they're doing is running the inverter in idle, which in a backup power system is the case at nighttime all the time. So the state of charge will say 100% because it never sees it discharge that battery. But once it gets too low, it could be really far off from reality. Where I've seen this a lot is where someone's turned on the inverter and then left it sitting there in standby for 2 or 3 months before they get permission to operate. So it's not really doing anything. It thinks it's at 100%. So the battery is not actually requesting a charge because it says I'm at 100%, but it's not really because it's been slowly running that idle load of the inverter for weeks and weeks. and you might be at 30 or 40%. Where you get in trouble is if you're way lower than the indicated state of charge and you've set your minimum discharge to low, you might be actually at 0% when it still thinks it's at 15 or 20%. So keeping them, making sure they reach 100% state of charge regularly keeps it more in calibration, but also keeping that minimum discharge a little bit of a floor off of 0% will help as well. We're working on improved firmware for the batteries, which will do that recalibration at state of charges other than 100%. So if you have a really slow discharge, it'll actually recalibrate and say, I'm not at 100% anymore, even though I didn't see any leaving. I'm seeing my voltage go down, so I'm going to recalibrate. But for now, this is a kind of endemic issue to all lithium batteries currently. There is this issue with very low loads can cause state of charge drift. Discharge SOC on grid is another really important one. This essentially is the reserve capacity that you want to keep for off-grid use. So if you're doing time of use charging or self-consumption on the grid, you're going to have a portion of your batteries that you want to use connected to the grid, and you want to keep a portion of it for off-grid use. If you're not really concerned about backup power during grid outages, maybe you set this really low. Say, I'm going to potentially set this at 20% because I'm going to use all of this just doing self-consumption or time of use shifting. That's what I want to use my battery for. If you're mostly concerned with off-grid, say you've got a battery backup system with net metering and you just want to keep those batteries full all the time, we want to set this discharge and SOC on grid or reserve capacity to not to 100%, because then we run into that state of charge drifting issue. But if we set it to say 95, 96, 97%, it'll draw it down just a little bit each night. And that gives it the signal to say, I need to be topped off the next day. So it charges it back up to a true 100% and recalibrates. If you actually set the reserve capacity to 100%, it'll never know to do that top off charge and recalibrate, and the state of charge can drift off from reality. We can set our maximum charge power, maximum discharge power. The Midnite batteries can charge at about a C1 rate, which is well over the capacity of a single inverter. So you don't really need to set this lower, but there's also no real reason to be cramming power into the battery. So you could set it lower if you want. if you have different batteries than ours that have a more limited charging or discharging rate, and especially with lead acid batteries, which have quite a bit more limit, or smaller lead acid banks, you may want to set these. Maximum discharge power, 10,000 watts per inverter gives you the full inverter capacity. If you set that lower, you can have issues with the inverter not really being able to run to its full capacity. This is per inverter for stacked systems, but it's for the entire battery bank. So that can be a little complicated to wrap your brain about. So if we've got, say, 4 batteries, technically we could do 4 times 16 kilowatts. That's a lot of power. But if we're setting it per inverter, we would set it to 10,000 per inverter, as long as that doesn't exceed the 64 kilowatts for a maximum discharge of 4 batteries. Still in the battery settings, we have charge by grid. This enables or disables whether we can charge from the grid. Even if we've got this disabled, that recovery charging, if the battery gets below that minimum recovery charge level, we'll still charge from the grid, but in general, it won't for anything else. This does vary its behavior based on the firmware version. Some firmwares, actually the latest 606 firmware, the charge by grid completely overrides self-consumption, which is not very useful, and we're working on a better system for that, which the charge by grid will only apply during charge time-based periods. The older 406 firmware, that is actually how it was, but we fixed a different problem and lost that functionality, so we're working on adding that back in. The stop charging by battery capacity is how high the grid can charge it. Now, remember, we've also set separately what's the maximum charge on the batteries, which will be 100%. But we could set here that we never want to use the grid to take them above 80% and let the solar do that top bit. And then, of course, we have maximum allowed charging power. This is from the grid. So the maximum charging power we were just setting on the last screen is from any source into the battery. This is specifically from charging from the grid. And then we have force charging, which essentially overrides a bunch of other settings from the grid or the generator if there's something that would keep it from charging, and this will allow us to charge the batteries. The most common use of this is if we know we have a storm situation or potential power outage coming up and we're using our battery for self-consumption, say, but we want to top it off to 100% because we know there's a storm coming and we want to make sure it's full for that. We hit force charging, it'll top it off. Once it gets up to the stop charging back by battery capacity, 100% in this case, it will reset and turn that back off. So it's kind of a one-time thing. This setting is also available on the interface for the end user, whether they're on the portal or the app. So the end user can go in and say, top my batteries off before the storm comes. Another use for force charging is if your settings are all messed up and it won't charge from an AC source, is to kind of override those and charge. That's not really the intended use of it. It's better to figure out which setting is keeping it from charging and change that. But that is something that people have been doing, is they don't understand all the settings, so they just hit force charging all the time to get it to charge. It works, but it's kind of the brute force method of just overriding incorrect other settings. Power control. Here's where a lot of different settings are. First is going to be our work mode. Do we want it off grid? Do we want self-consumption or grid feed-in priority? Grid feed-in priority is really just for systems that don't have batteries, where you're using the inverter just as a straight grid tie inverter. And it's basically prepped for adding batteries in the future. It can also be used for net metered systems, but it has some problems with the state of charge of the batteries and state of charge drifting, which are better addressed by setting it to self-consumption with a reserve capacity at, say, 96%. Self-consumption, what it does is it tries to power loads from the batteries first, unless it gets down to that reserve capacity, and then it'll switch to powering them from the grid. It can be used for where you don't want to draw from the grid, or when combined with some of the time use functions, it can be used to just draw during certain times of the day from the batteries instead of all day. Off-grid is useful for off-grid systems, obviously, But it can also be used for zero export systems, especially if you don't have an interconnection agreement and the utility doesn't know that that system is there. You may want to hook your grid up to the generator input where it can never export to it and it doesn't operate in parallel with that. And operate it that way rather than doing a zero export in self-consumption grid connection. Because there, the inverter is operating in parallel with the grid. And technically, even if you're doing zero export, you're still supposed to have an interconnection agreement with the utility and have them know about it and all of that. If you want to do it without them knowing about it, doing it as an off-grid system with the grid connected as a generator is really the only safe way to do that, because then you're never operating in parallel with the grid. You're only using it as a charging source, just like any other battery charger connected to the grid would be. For self-consumption systems, we have normal loads. Normal loads are our grid-connected loads that are not passing through the inverter and are not on the backed up loads panel. So they're everything else in the house other than your backed up loads. The inverter, through the CTs, can see what are those other loads, and it can export just enough power to power those normal loads instead of having power coming in from the grid for those. So it's not selling power to the grid, but it's exporting enough to support the other loads that are in between it and the grid. This relies on the CTs being hooked up properly and a bunch of other settings. Take a look at our webinar on CT placement and programming for more information on that. Another thing is that AC coupled PV generally needs the support normal load enabled for it to work properly if you have a grid tied system. And I think that's it on normal loads. Zero export, that's mostly self-explanatory, other than that it can be the reverse of what you think. You enable zero export to prevent selling power to the grid. You disable zero export if you want to sell power to the grid. There's several other settings for it to actually work properly. It's not just clicking zero export. And if you're in off-grid mode and you're using a generator on the AC input, you also want to make sure that you've selected zero export to make sure you never export power into that generator. Generators really don't like that. Or zero export or support normal loads, anything in self-consumption requires the CT sensors to be installed. And you'll need to set where they are, which direction, and have everything installed properly. It's very important that L1 and L2 are correct. They're not interchangeable. And the little arrows on the CTs have to point the right direction. Again, this is another webinar on specifically on the CTs. Power derating control method, don't change that. Maximum feed-in grid power. This is where we also set this to zero if we're doing zero export. If we have a limited export, say the utility says you can only export 6 kilowatts because of our transformer size, this is also where we would set that. If you have CTs that are supporting normal loads, this is the export to the grid. So the inverter might be exporting more power than that, but it's being used by other loads in the grid connected panel before it goes out to the grid. A very important one, if we're doing zero export, is maximum consumption from the grid, which is not at all what the name implies. This is actually a minimum import from the grid to make sure we don't overshoot zero. So instead of going all the way to zero import from the grid, it actually goes to this level where, in this case, it's still importing 30 watts from the grid at all times. And the reason for that is if you've got a large load that suddenly turns off and it's powering a bunch of loads, say at 8 kilowatts, and 6 kilowatts of that load suddenly just turns off, it takes a second or two for it to respond and get back down to where it should be to keep from exporting, especially if those are motor loads with a lot of inductive component. It can take a bit for it to respond. Now, a second or two isn't that long, but the new smart meters can see that second or two of exporting to the grid while it stabilizes, and you can get in big trouble with the utility company if you're supposed to stay at zero export and they see you doing these little blips of export, especially if you didn't tell them you have a PV system at all. So the way around this is to always have a little bit that's being imported from the grid. And then if you've got a bunch of load changes, those little kind of blips up and down stay below zero instead of going above zero and exporting a little bit. It depends on what kinds of loads you have. Generally, I've found that you need to have somewhere around 100 watts per inverter to prevent this. If you've got a lot of big loads turning on and off all the time, you may have to go a little higher. If you've got really uniform loads, you might be able to go low as the 30 watt minimum. But that's what this is essentially your minimum grid import to keep from accidentally exporting when you're supposed to be doing zero export. Time-based control is what we use when we want to do different things, different time periods of the day. Usually when we've got peak rates during certain times of the day. Time-based control overrides self-consumption mode. So self-consumption is trying to power all the loads from the batteries rather than drawing from the grid. But what if, say, you've got a peak time between 5 and 9 p.m., and that's really when you want to use your batteries to power the loads. After 9 p.m. and before 5 p.m., you don't care so much. So what we do is essentially use our time-based control to override the self-consumption when we don't want it drawing from the batteries. So we set a charging time period from midnight until 5 p.m. and then another one from 9 p.m. till midnight. And during those time periods, we've overridden our self-consumption and it will charge the batteries from the solar if we've disabled charge from grid, or from the grid if we've enabled charge from grid. We're working on newer firmware where we can individually set on each time period, do we want to charge from the grid during this time period or not? And that could be useful if you have, say, a peak time period, but you're also in a situation where you're faced with potential power outages and you want to top those batteries off in the middle of the night from the grid and make sure they're ready for a potential outage, but you also don't want to be drawing from the grid during that peak time rate. Right now, the software doesn't work for charging from the grid when you're using time-based control and self-consumption. The charging from the grid just kind of overrides that. But we're working on fixing that, so a newer software version will have a lot more functionality here. But for now, you can set it so it'll use self-consumption during those peak times, and then by setting a charging time period during the rest of the day, it will charge it back up from solar only during those time periods. Discharge time periods, they always discharge at the specified wattage. So this is when you have, say you want to sell a specified amount into the grid or offset a specified amount from the load. Maybe you have too big of a load to do self-consumption for the entire load during your peak times. But if you could take 5 kilowatts off of that load during those peak times, that would be pretty good. So in this case, we could set a discharge time period during those peak times for 5 kilowatts. Now, if our load is less than 5 kilowatts during that time, it's going to still discharge the batteries at 5 kilowatts, and that any extra over the load will end up being sold to the grid. If you've got a utility rate where you're allowed to sell batteries to the grid, you could say, I want to sell my batteries at 10 kilowatts for this 2 hour period because I'm getting a really good rate from the grid if I'm selling during that period. So you could set, I want a discharge period from 6 to 8 p.m. at 10 kilowatts and just drain my battery because they're paying me $1 a kilowatt hour because it's their peak time and they really need power. But if we're just trying to cover our own loads, self-consumption will follow along the loads rather than just discharging at a specified rate. We can also set the state of charge where this stops at. So we could say discharge from the battery at this rate, but don't draw my batteries all the way down. I can independently set it at a bit higher level if I only want to do it for a short period. For all of our charging and discharging things, we can set what state of charge we want to stop that process at. For charging power, once we get the firmware updated where you can individually select charging periods for charging from the grid, you could say use self-consumption during a high time of use rate, and then immediately once it goes to an off-peak rate, recharge the batteries back up to say 70%, so you've got some reserve left, but then keep some in there, but not use the grid to completely charge them up and wait for the sun to come out the next day to fully charge them to 100%. Smart loads. So we've got 3 smart loads on the inverter. Smart load 1 can either be a smart load, 60 amps, or it can be the generator input. Smart load 2 can be a 50 amp smart load, or it can be your AC coupled PV input. And smart load 3 is a 30 amp smart load. These are 240 volt output breakers, and they can be used directly or they can be used to control the 120 volt or 240 volt coil of an external contactor to do further controls. Each of these smart loads has a start and stop state of charge, and the way these work is it's on until it drops below the stop state of charge, and then it stays off until it rises above the start state of charge. So in this case, we get 40 and 55%. That means it stays on until it drops down to 40, and then it'll be off until something recharges it back up to 55%, and then it'll turn back on. So that's the logic of how these work. Examples of how to use these smart loads. We might use them for less important backed up loads. So we've got our backed up loads, and then we've got some that, as long as we've got lots of sun or the batteries haven't been depleted, we want to run some like less important things as well. So we might set it at 60%. So once it drops down to 60%, we kind of dump a lot of our less important loads, keeping a lot of remaining capacity for our more important uses. If we have a short outage, we may not even get down there. We keep everything on there. But if we have a longer outage, we kind of dump off some of those loads. This could be used for an off-grid situation where you've got a bunch of different category loads, and maybe our main loads panel we let stay on all the way down to 10%. But we have some less important loads that once it gets down to 75%, we're like, yeah, we're dumping off the big screen TV now. You don't need that during a snowstorm, or depending on what you want to do. So it could kind of automatically manage some of your loads by staging them for an off-grid system. Another use example is as a dump load. So say when we've got plenty of electricity, we want to turn on EV charger or turn on a water heater when the batteries are full. So we might set it at 95 and 99%. So anytime it's full, we've turned on that dump load. Once it drops down to 95%, it shuts it off. If it charges back up to 99%, turns it back on. We want to leave a little bit of room between there just so it's not going on and off too quickly. But that's a means of using our smart load control to essentially be a dump load when we have excess solar and our batteries are full. For our AC coupled PV arrays, we have similar control for when we turn that AC coupled PV array on and off. And this one's similar, but it's kind of the reverse. We've got a stop level where we turn that PV array off, and then a start level where it turns it back on when it drops below that. So generally we'll want these both to be pretty high, usually 100% for the stop, and then high 90s somewhere for the start. Remember that you're also going to have a 5-minute delay on most grid connected inverters that are on that AC coupled PV array for it to turn back on after it sees power again, after the all-in-one has turned on power to that relay again. One problem we've seen a lot of people having understanding the logic of this is that these are start and stop points, not the points between which that it operates. So I've seen people set the start one all the way down at 10%, which means the batteries are going to have to drop all the way to 10% before it starts charging again. That's why you want the start one up there quite high. So if it does shut off, it'll turn back on once the batteries start discharging any appreciable percent. It will also do frequency shifting if you've got new modern SunSpec inverters that vary their output based on frequency. So that generally starts at 5% below the stop SOC. So in this case, if we've got our stop set at 100%, once it hits 95%, it'll start frequency shifting that to start throttling back the incoming power from the AC coupled PV array. In that case, we want our start a little bit less than that, maybe put it at 94%. In that case, it should just frequency shift and never actually completely shut off the AC coupled array. Obviously, it can only do frequency shifting when it's connected to, or when it's not connected to the grid. When it's connected to the grid, it always just sells the extra power to the grid. For our generator, we've got a number of settings. We've got our maximum input power from the generator, as well as our maximum charge power from the generator. So the charge power is how much it's using to charge batteries. The input power is the total it's drawing from the generator for batteries plus the load. It'll back off on the amount that it's using for the battery charging if the loads are using too much. Then we also have our start and stop state of charge. And these are kind of the same logic. When the state of charge drops down to the start state of charge, 30% in this example, it will start the generator, and then it'll run the generator until it reaches the stop state of charge, 45% in this example. Now that's for a generator that's auto started. Our dry force is set to auto, and we're connected to terminals 1 and 2 on the dry force going out to the generator. If we have a manual started generator, we've got a little bit different logic here. There we need to set the drive force to on, and it's not actually controlling the generator, but by setting it to on, it's telling the inverter use your generator input, because it's actually a multi-function. When it goes to on, it's not only sending a signal out to the generator, but also telling the inverter close the relay to the generator input and use that input. Also, the state of charge needs to be below our start state of charge for it to use that generator. Even if it sees it, it won't use it if the state of charge is higher than our start state of charge. So in those cases, we would want to set our start and stop state of charge really high, usually say 90% and 100%. So then when you manually start the generator, anytime it's below 90%, it will use that generator to charge until it hits 100%. And then it won't shut the generator off because you manually started it, but it will stop using the generator. So if you've got the generator running and it's manually started and it's just not charging, often this logic is one of the issues. That either the drive force is not set to on, or your start and stop state of charge are set too low, and it hasn't, and the actual state of charge is higher than that. We've got our standby time. That's the cool down time after it shuts the generator off if it's auto started. Max runtime is the max runtime each day. So if you've got, say, a small battery bank and a heavy load where you're starting the generator more than one times a day, that max runtime needs to be set to accommodate all of the run times that day, not just one time. Drive force control is our output, which controls our output to the generator two-wire start, but also tells the inverter to be ready. So, like we said, keep that to on if you're using a manual generator, and put it in auto if you're doing a automatically controlled generator. And then we have a run cycle for exercising the generator. And that wraps up all of our normal settings we go through. Please email me with any questions you have on settings, and we will see you next week.